Good morning, everyone. In this video, the main objective is to find out the step response of a system which is modeled by a Simulink model. And basically, the objective is to derive the output variable from Simulink to workspace, and from that output variable to find out the corresponding step response to system. So, for this purpose, what we have done, we have taken again, we have referred this paper and taken this automatic voltage regulator system, which is modeled by as follows. So this is the APR system, and this is the block diagram modeling of the APR system. So this is the input reference voltage. This is the output voltage that has to be controlled for that APR. This is the sensors, amplifier, exciter, and generator model by this transformation. And what it is given, then the range of the amplifier, all these values have been mentioned over here. The range of the amplifier is in between 10 to 40. And in this model, they have utilized it 40 and the time constant, that is the value of Ka, and the time constant Ta value, that could be possibly in between 0.02 to 0.1. And they have taken a value of 0. Likewise, the value of Ke, Kg, and Ks is also been mentioned. Similarly, Te, Tg, and Ts is been mentioned like that. So these are all these values that they have taken in this paper, and we are supposed to model this one. And after modeling, we'll verify that whether this kind of step response with all this step response information is being achieved from that model or. So for that purpose, let's first do it by MATLAB. Then we'll verify things using Simulink. Now, so using all this data, so what we have found, if you multiply, you have to put all this data and you multiply, all these three blocks are in cascade, so they could easily multiply to each other. So the overall forward path gain is as follows. So this is the overall forward path gain that will found out to be 250 divided by this factor. And the sensor gain, we have kept as is, this is the feedback path gain. We have kept as is in this bit. This is the feedback path gain. Now, so let's first model it by MATLAB, then we'll do it in Simulink. So if you do the programming in MATLAB, so first of all, we have to write the transfer function, and then we'll find out its corresponding step response and step response information. So let's say in this forward path, we are having a forward path gain that is G of S. Then you have to model that one. Let me take a numerator polynomial and the denominator polynomial. So the numerator polynomial here is 250, and the denominator polynomial here is in form of a matrix that is 1, 13.5, then 37.5, then 20. So this is the denominator polynomial. This is 1, 13.5 here, 7.5, and 25. So there is the denominator polynomial. So let's get the forward path transfer function. Let it be G equals to TF. So we are doing it by taking the numerator polynomial and the denominator polynomial. So this is the corresponding forward path transfer function that we have just taken over here. Then the feedback path transfer function, let's say this is numerator 1 or numerator 2, whatever. Let's say numerator 1, that is, let's say that is 100. Likewise, the denominator that is and so feedback path transfer function that is given that is this transfer function numerator 1. So this is the corresponding sensor transfer function or feedback path transfer function. Now the overall transfer function of this closed loop system, let's say B, and it's a negative feedback system. So the command is feedback. And keeping the forward path KNG, feedback path KNH, and by default is a negative feedback system. So this is the overall transfer function. And if you want to find the step response of this system, so step of T, so this is the corresponding step response of the system. This is the corresponding step response, and the similar information is used as obtained paper as well. This is the step response of this system. And if you want the corresponding step response information, so that also you could get both the characteristics, that is the rise time, then the settling time, let's say the steady state value, see the peak response as well. So the corresponding rise time is found out to be the 2.0.261 that is mentioned over here, 0.26. And again, similarly, the peak amplitude that is 65.7% overshoot and peak amplitude is 0.1.51. So that is overshoot 65.7%. That is mentioned. The settling time 6.9, the settling time 6.9. Here it is 4%. And the steady state value is 0.909. So that is why there is a steady state error, that is 1 minus 0.909, that is 0.09 steady state. Now let's take all the state data, and again the same thing could also obtain by the command state of the closed loop classification. All the same details can be obtained at this. Now the objective is to bring the same information on the Simulink. We have designed the Simulink model this one, and all the forward path transformation we are multiplied to the now, if you want to take the step response, it is some people take it by using a step signal. So the step signal step time is 0, it is a value another 1. Or some people also for a constant value of 1, both the ways are possible. So in both of this is the forward path transformation. This is how these things are been defined. Likewise, is the feedback path transformation 6. Then the corresponding output response of that APR system that we have taken is the 2 workspace block. We have to bring this system to bring this variable to this so that we convert on that. And the variable name is taken P. And here there is you have two choices. We will demonstrate this by taking a time series as well as a time. So let's first go for a time series method, then we'll so that this variable B is in a time series. Likewise, let's take this the clock out and let's take the simulation time to Aj output variable. So that is why variable is time, it is time series. Okay. And this is a dashboard score. Whatever score you want, this is the same thing. The dashboard is so that you will visualize this in those periods. And the simulation time we have taken 15 seconds. Because why we are taking it from that paper itself, because we found it is coming under the steady state in between 10 seconds, 15 seconds like that. So simulate this system. This is the same result, whatever we have got, some same step response, and this is the reference. To input the step value, that is 1, is the corresponding step response. Blue line is GMS, and the straight line is the step signal that is given to the system. Same thing you can see. Same information. So this is the same step response. Now, we have taken this variable P to the output in form of a time series. So let's plot it in that output variable. And let's see the steps. Now, as we have, there are some commands I have created. Let's take that in. So here, let's first plot the output variable and see what is the corresponding step response information. Now, we will plot that. See the as we have taken the variable time series. So the command is plot out dot is the variable, and again you notice the time series format we have taken the variable. So here it is this And we'll see here. This is the V variable, which is we have taken in from time series, and this is the time. Now, if you click this key, this output variable. So, what we'll find that it is in form of a column data, and it is having data. First is the data value, and the time. So, whenever it is in time series, what need to take the time again, because already it is coming with the time series. So that is where what is given dot output key dot time. So this is the time variable with respect to dot output key dot is the data that value, and it is giving you the corresponding step response. Now, if you want the corresponding step response information, so what we're supposed to find, this is step in. So first of all, the output variable, that is output p dot data. Just time we are finding it. So this is the corresponding step response information, and how we got it? We got it basically from Simulink. But to verify both the things, there is a marginal error. Yes. This information we have got from the MATLAB by taking the step response step input, and this is what we have derived from simulation. Now, if you see the rise time is same 0.26, 0.26, but there is a little bit error in the settling time. The settling time is 6.98, around 7 seconds. But here it is settling time is 7.5. So there is a error of 0.5 seconds. But if you see the other parameters, settling mean this is 0.4, this also 0.48, settling maximum 1.5 below 1.5 below, should be 65.72%, 65.78%. Peak amplitude 1.5 to 1.5. All are same. Peak time is also same 0.75. This is a little bit marginal error this exists in this. Now let's do one thing. Let's convert. Let's take it in form of. First of all, we have seen that how to convert it in form of time series. Let's change it to array and just find the same visibility. And just notice one thing, if it is in time series, we do not need this clock and time thing, because already in time series format, the variable p is coming with the time series. So we don't need this value. But if you take it as array, then we need this because time has to be. Now let's change this. Instead of time series, make it array. All other values need to be same. Likewise, here as we're only taking it in form of array, so we need a time as well. So this variable time. Now if you simulate this one, see same step response we are getting over here. And again, you could also verify those things by clicking the constant block as well. Change this switch to constant. And if I run it, the same response. Now let's as the model was in form as the signaling is in form of the array. So let's go further and take this one. Now, as you have we have taken it in form of array, so keep it on change of command. So this is plot, and again, if you just check it again for this output variable, and here it is key. Just notice here E only comes with it is a single dimensional thing, and it is only comes with the value of that not the time. That is why we need again the time variables. And then you can check the time. So we need the time variable. So to the block we need at this point of time. So here it is plot output key. We do not have this time. Sorry, we do not have this time stamp. So this is output key. This is output time. But again, this is key, this is time. Because why? Because we have the plot x-axis versus y-axis. So this is the corresponding time response. And if you want to do corresponding time response information or step response information, then it should be stable. And this is the first output variable that is output. We are finding out the time is by this output. So this is the corresponding step response information. And if you verify again, this was the time series format and this is the array format. And it is the similar because same 0.26 rise time, 0.26 rise time, conjugate time, cyclic time, right? So here we had the array parameter. But rest all other parameters the same. 65%, 65%, so like this, we could take and we could work on any Simulink model, bring those variables to the workspace, and we could find, we could manipulate on that, we could plot of that,